Good afternoon. Afternoon, everybody. Before I start the lecture, the assignment, I can't remember the percentage for it, but there's a model analysis assignment that will be due in a few weeks' time. So I'll put up details about that tomorrow. So it'll be up from tomorrow, and then you can look at it and start to work on it. So you'll have a Fluent lab this week, and then next week will be a week off. So in your timetable, there will be a lab, but week 8, there's a gap before we start OpenFOAM, and that allows you time to work on this model analysis assignment. So I know a couple of people have contacted me, so I'm going to put it up tomorrow. But essentially, it'll be an analysis you have to create and perform in Fluent, and you just have to try address a couple of questions. I think 5 or 6 questions. It's not like a big report. I don't want a bunch of text. It's just set up the model and then look at like mesh sensitivity analysis, look at things like that, and just show me you can do that. That's basically the idea of it. When I put it up, if you have questions about it, feel free to come back to me and I can clarify anything that's not clear. Any other questions about the labs or anything else? Everything's still fine? Okay, nobody says it, and I assume it's fine. So today I'm going to talk more about finite volume method, which is what Fluent is based on, and OpenFOAM is based on as well. So it's more popular for computational fluid dynamics. But as I said, it can be applied to solid mechanics the same way finite element can be applied to fluids. So the last day we had a look at the finite difference method, this kind of older method, which is still popular, and how if we have a nice structured set of points, if we took, this is called the diffusion equation or the steady state diffusion equation, representing flow of, say, heat or temperature into a point, we showed how you could discretize this on a grid like this. So it's basically in component form, it's the second derivative in the x plus the second derivative in the y is equal to 0. And then the question was, well, at a point like point P, this red point in the center, how can we approximate this in some way? So we showed one particular method for approximating that, and we got it looking like this again. So we were able to write that equation in discrete form at this point in terms of the mesh spacing, the delta x and the delta y, and in terms of the values of phi or temperature at the different nodes, north, east, south. Then we subsequently went on and applied that to the finite volume method, and we showed how that was different. And the idea with the finite volume method is it's written in integral form. So rather than at a point, we use this integral equation and we sum what's flowing in and out of the surfaces of a cell or a control volume or an element. And for a structured grid like this, we showed that actually it ends up giving you the exact same form as a basic finite difference method. And this is how far we got the last day. That if you designed on purpose a grid like this with finite element, you actually end up with the exact same equation for this center node. But in general, they're not exactly the same. Okay, so for the rest of the slides today, I'm going to just talk about some characteristics of finite volume methods and relative to finite element. And then I'm going to end by talking about how specifically they're applied to the Navier-Stokes equation. So when we're using Fluent, how exactly is Fluent doing this? So if we stick with this, our basic diffusion equation, what Fluent and OpenFOAM might use is what's called a cell-centered finite volume method. So for any cell, you can see it's a triangular cell here, and we have the unknowns at the centers of the cells. That's why it's called cell-centered. So just some naming conventions. Where the equation is applied is called the integration volume. So in finite volume method, you're integrating over this cell like that. And then we're writing this equation in terms of the unknowns at a particular set of cell centers. So that particular set for that cell is called the computational stencil. Sometimes it's called the computational molecule. And if you're using a higher order finite volume method, then the stencil tends to get bigger, so you can fit higher order polynomials. But there are other finite volume methods. So there's vertex-centered finite volume, which is not the same as finite element. So you can store your unknowns at the vertices of your mesh, and then you can integrate over what they call a dual mesh. So they will make a control volume around each of these nodes, and they integrate what's flowing in and out of each one of those. And then for contrast, finite element method, we took each of these elements, we formed a stiffness matrix, and then we assembled them together, which basically gives you a balance equation for a particular node. So there's a contribution coming from each of these elements to the balance of heat or force for this node. So it's useful to see the difference in integration volume and computational stencil for the different methods. So the integration volume for finite element is all of these elements around a node. Where cell-centered finite volume is just the cell itself, and vertex-centered finite volume is this dual mesh. Dual is in D-U-A-L, not joule. And it's very faint here, but if you look at neighboring integration volumes, it's very, very faint, apologies. There is another cell drawn here. So in finite volume, the neighboring integration volumes tend to not overlap. So whatever flows into one flows out of the other. Whereas in finite elements, they overlap because elements are shared. So this is why finite element is known as a non-locally conservative method. So what's flowing into this cell into the integration volume from this cell to that cell, since they overlap, it's not exactly locally balanced. So this is historically why finite volume methods were preferred for fluid analysis. But that's no longer the case. They've come up with smart ways to solve this. Some other just characteristics to note, if you look at the boundary of the domain, in cell-centered finite volume methods, you know nodes or unknowns on the boundary, whereas in vertex-centered methods like finite element and vertex-centered finite volume, you do. So it has some consequences for how easy it is to implement boundary conditions. And there's a variety, a continuum of numerical methods of different ways to deal with these issues. Okay, so I'm going to talk now specifically about the Navier-Stokes equation. So what is Fluent doing, and what OpenFOAM, which we're going to get to, does when it's solving these incompressible Navier-Stokes equations. So just to remind you, these are the incompressible Newtonian Navier-Stokes equations, and they're isothermal as well. Isothermal, I mean we're ignoring temperature. So far what we looked at for the finite volume method is this diffusion term. So if we just let all the other terms equal 0, this diffusion term, this velocity here could have represented temperature or something else. So we actually have covered how to discretize this particular term and how Fluent might do it. So this represents the viscous stresses, if you remember from previous lectures. These are the surface forces. There's viscous forces, pressure forces, body forces like gravity. And this is mass by acceleration, written in this Eulerian form because of this Reynolds-Stokes formulation. Or Reynolds transport theorem. So for the finite volume method, we always start with the integral form of the equations. So if this is the differential form, as in without integrals, they're applied at a point. So these equations, these Navier-Stokes equations, must be satisfied at every point in our continuum. But equally, if we add a bunch of these points together, they must also be satisfied over a finite number of these points. So over some finite region of space. So this is integrating over some volume. That volume could be a cell, it could be the whole domain, it could be some subset of the domain. And these are all integrated over volume. So if we just integrate each term over volume, that gives you an equal. But a characteristic of the finite volume method is anytime you have a divergence, so divergence here, or a Laplacian, which is a divergence of gradient, and the characteristic of the finite volume method is you use the Gauss theorem to convert those to surface integrals. So here's a divergence here as well. So that anytime there's a divergence, you can change this to a surface integral and replace it with the outward facing normal on the surface. And that's just a mathematical equivalence. It basically relates what's happening at the surface of a finite region to what's happening inside it, and they have to be equivalent. So in the next set of slides, which I'll open up, we're going to go through how these individual terms are discretized using the finite volume method in softwares like Fluent and others. But before doing that, it's worth pointing out the different types of terms that we have. So specifically, we have two types of term. We have volume integrals and surface integrals. So an integral here with a omega that's integrating over the volume. So things like the body forces adding all the gravity contribution across the volume. But then we also have a closed surface integrals. So this circle means it's a closed surface. So we're going around the surface in space and we're adding up what's flowing in and out of that surface. So in this case, we might be adding all the viscous stresses on the surface. And then this advection or convection term, it's adding up what the flow of mass or momentum is through the surface. So in the finite volume method, we will deal with the surface integrals and the volume integrals differently. So we'll go through basically how to discretize each of these terms, and once we've done them all, that shows us how it is done for the entire equation. So I will click to the next slides. Hide this. Okay, fine. I can send this. Okay, I'm going to start with volume integrals. Volume integral, I'm going to write just a generic one. So if I integrate something, I'm just calling this something phi. Well, imagine that something phi, I want to integrate it over volume. So this phi could represent any of those terms that are being integrated in this equation. And in its continuum sense, that could represent something that varies in space over the domain. Let's say it was just the temperature. The true temperature solution might vary in some way, like a polynomial or a sine curve or something more exotic over a particular space. So for the self-centered finite volume method, the challenge is, if you have a structured mesh, is how can you write this term apply just to this control volume, to this cell here, and write that in terms of a particular computational stencil, as in the values of either phi or the values of maybe phi is a function of what you're solving for at these particular locations. And just to give it more general, that, okay, our actual mesh might look like this. So one maybe benefit of the finite volume method is it's can deal with semi-arbitrary cell shapes. So for example, here, what's that, a hexagon? But in 3D, you could have a dodecahedron, or you could have all sorts of unusual shaped cells. And that's fine for the finite volume method. So when you see we go through this, we will make no specific limitation on the type of cell we can use. Whereas in finite element methods, you need to come up with our interpolation functions that exactly match a triangle or a square or whatever. So this is, in the literature, maybe one claimed benefit of the finite volume method, that you can use arbitrary meshes. In practice, I don't know if it makes a big difference, because you're limited by the measure, what measure. And there are exotic finite element methods out there. So in the finite element method, we derive a stiffness matrix for each particular cell shape. We looked at triangles, we had unknowns at the corners, and we assumed a certain variation within that triangle, and then we fully characterized or discretized what happened for each element, and then we assembled those together to figure out what was happening for each particular node. But we don't do that in finite volume method. So we treat all cells as just general polygons or polyhedron in finite volume method, and we integrate the volume integrals over volume, and the surface integrals we go around the faces. So let's show how that works. So one of the early steps in the finite element method is we assume the interpolation function. So the true solution, displacement, temperature, whatever, pressure, it will vary in some way that we don't know. Maybe it's some higher order polynomial, and some function we're not aware of. So maybe that could be represented by this blue. So in the finite volume method, we don't assume an interpolation function directly in the same way, but we do something equivalent. So we're going to use this expression here, which is called a truncated Taylor series. So the idea of a Taylor series, or a truncated Taylor series, it says that if you want to define a function in some area close to some point, say we're near some point P, and I want to write give an expression for that function in terms of only values at that point, values at the point of gradient. So a Taylor series says that you can write that the value approximately of this blue function is equal to the value here, plus extrapolating linearly from that point using the gradient at that point, plus using the second gradient at the point, plus the third gradient, plus the fourth gradient, and it goes to infinity. So you can represent most functions if you have enough terms using this Taylor series. So truncated Taylor series means you just truncate, you get rid of some of the terms. So this second order approximation, or sorry, first order, is you would say the value of phi close to this point, and this blue region, approximately, this should be an approximation, is equal to the value here, plus how far we are from this point. So x is the point we're looking at, say this point, say here. You can say the value there is just an extrapolation. So take the gradient at that point times the distance. So if you multiply the gradient at this point by that distance, that's basically how much is changing based on the slope. And so using this truncated Taylor series, you can say that the value anywhere here is just like a linear extrapolation using the value here and the gradient here. So we're only using the value here and the gradient here to get a linear approximation of the function in the neighborhood of that value. So you can imagine if we also had plus, it would be x minus xp squared over 2 by the second gradient. You could add a curvature term and you could get even closer. And you can keep adding more and more terms to get a closer approximation. So one of the key components of many finite value methods is within each cell, we're going to use a formula like this. We're basically just going to say the value within each cell is just equal to the value at the center of the cell, and we're going to extrapolate from the center using the gradient at the center of the cell. So that means we only need the value at the center and the gradient at the center, and then that's enough to get rid of the continuous function. So that should be an approximation term. So we're saying the value of phi, whatever we're going to integrate, is just is a function of x, some coordinate. And we can approximate that by just taking the value at some point and the gradient at the point and extrapolating in any direction. Obviously, the further away we get from the point, the worse that approximation becomes. So if this blue line curves back down like this, if we try to just use the gradient here, we'll extrapolate and get a value up there. So that obviously won't be very good. But at least in this region, the error will be bounded. And we can actually show that the error will be second order. If we have that spacing, it's actually a second order approximation. So this linear distribution produces a discretization error and reduces at a second order rate as the distance is reduced. So that's actually the same as linear interpolation functions in the finite element method. So even though this doesn't look the same, this is equivalent to linear interpolation functions in the finite element method. So when we assume the function form in the finite element method, we're essentially doing the same thing here. And what does second order rate mean? It means that if we half the spacing, this approximation error, it becomes 4 times smaller. So you can kind of see that distance there, if you half the spacing, that error is not half, it's much less than half. So it's actually 4 times. And you can also have an idea of where the asymptotic region is. So once we're kind of below the top of this curve, we're kind of in an asymptotic region, but once you go outside that, it's no longer asymptotic, the error can get bigger or smaller. And we can't be sure that. Okay, let's go back to this term. And we want to apply this term. So the idea is take this true solution, which we don't know, and then we'll approximate it. Once again, I should be using strictly an approximation sign here, not equals, and just replace it by the value at the center of the cell plus some extrapolation using the gradient at the center of the cell. Okay, so I decided to use it this time. So if I just substitute that in, so this is kind of like our, once again, our interpolation function, our functional form. We're subbing it in the same way we did that for the finite element. So we're going to sub that in, and it looks like this. So this is going to make a second order finite value method, but if we include a square term, that would be like equivalent to quadratic elements. A cubic term would be like cubic elements, etc. So you can make higher order finite volume the same way you can do it for finite element. Okay, so let me simplify this. So we have phi p, that's just the value at the cell center. That's a constant, as in that will be some value which is just a number. Phi p is not a function that varies over the space of the cell. It's just the value at the cell center. So it's essentially like a constant for the integration. So that means that can be brought outside. So if I split it into this term and this term, so for this one here, integrated over the volume, I can just take phi p outside the volume. So it's just integrating 1 by the volume. That's the first term. And then the second thing, we have x, which varies in space. We have to integrate over x. So x, the coordinate, will vary over space. And this is x, the vector, so it represents x, y, z. But we can take this gradient outside because that's just, once again, it's just the value at the cell center. So it's not a function of x, it's just the value of the cell center that can be brought outside as well. So I split this into 2 terms and brought this phi outside and brought this gradient. So if I look at what's in the second integral, I'm integrating the difference between any coordinate minus the center of the cell, or the centroid of the cell. So that's actually the definition of the centroid of a space, or the center of a region of area or region of volume. So by definition, the point which satisfies this equal to 0 is the centroid. So we've already selected that, and this is why they select that. So xp is the center of the cell, or the centroid of the cell, the geometric center of a shape. And so x varies as we integrate over volume. So this volume is integration of x, y, z. I'm just writing a shorthand here. So by definition, if you integrate that thing over a particular area or volume, it is just equal to 0. So that means if this is equal to 0, then it doesn't matter, that gradient drops out. So we only have the first term. So if we only have the first term, we can approximate something, some field phi, over the volume by assuming this linear interpolation form. This thing drops to 0, and then this term here, you just integrate 1 times the volume. That's just the volume by definition. So that means that the term just becomes the value of phi at the cell center, p, by the volume. So omega p represents the volume of cell p, and phi p represents the cell center value, phi p. So actually, after all of that maths and playing around, if you have a volume integral term in the finite volume method, you essentially just drop the integral and change and just multiply by the volume and use the cell center value. So it's actually very simple. So if you have any term you want to integrate over volume, just calculate at the cell center, and then that is essentially a complete. So we're going to do that for volume integrals. So let's go back to our average flux equations and check where the volume integrals are. So the continuity equation, mass or volume conservation, that's a surface integral, so okay, we can't use it there. We have this transient term here, this is our acceleration. So that's a volume integral. So if we want to evaluate this, we have the acceleration. So if we just calculate the acceleration at the center of the cell and multiply by the volume, that's at least partly discretized using finite volume method. We have 1 over the density by the gradient of p. So if we just evaluate that at the center of the cell, multiply by the volume, and then we have any body forces like gravity, we just evaluate that at the center of the cell and multiply by the volume. That's consistent with the second order finite volume method. Depending on the books you're reading, it can also be shown that the value at the center of the cell is equal to the average value in the cell. So some people would present it as multiplying by the average value in the cell. But the average is the same as the cell center value in this formulation. So this is called transient term, pressure forces, body forces, surface viscous forces, and this is this advection. So we derived out this expression using this truncated Taylor series. So the pressure force, we can just apply that. We run over the density integration of the gradient of pressure. So we can just evaluate the gradient of pressure at the center of the cell, P, which we're going to call it here, and multiply by volume. So that's a second order approximation. And the body forces, FB could represent gravity, like G for gravity. So just evaluate that. It could be varying in space. In this case, gravity would be constant, but evaluate it at the center of the cell and multiply by the volume. And the goal of this discretization process is the unknowns, which for incompressible Navier-Stokes are the pressure at the cell centers and the velocities at the cell centers. So write these equations in terms of the velocities and pressures at the cell centers around a particular cell within the molecule. So by that definition, we haven't quite got there. We have a gradient of P, gradient of pressure at the cell center, but we still need to write that gradient in terms of the values at the cell center. So that's almost done, but it's not completely done. So there's a second step for that term. This step is done, and the transient term is the last one. So we just evaluate the acceleration, the d velocity dt, evaluated at the cell center, and multiply by volume. But we still have to discretize the velocity time, like we did for the dynamic finite element method. We have to approximate it at particular time points. So if it's velocity, the simplest way to do that is simple linear variation of time. So this is called Euler's method. So we can just say it's in terms of the t could represent a nu or the current. So the value of velocity at the current time minus the value of velocity at the total time at this cell center divided by the time step. So that's a first order approximation. So for the transient term, that's it done. That's it complete for that term. And the body force term is done, but the pressure term we have to still complete. So when you look at the discretization error, I focus on the spatial discretization error, as in when you make your elements smaller and smaller and smaller, this mesh error goes smaller and smaller and smaller. But you have the same thing for a dynamic problem. So in dynamic problems, you split time into these increments. So if those increments are too big, you might have large temporal or time errors. So you can actually apply the GCI method as well, where you would run 3 analysis with 3 different time steps, where you keep halving the time step, and you can show that the time error also goes to 0. So the GCI method can be applied with time steps as well as mesh spaces. All right. Back to your number 6 equations. So we've done volume integral here for the transient term. Done the volume integral for the pressure gradient term, the pressure surface forces, although we haven't written the gradient of pressure at a cell center yet in terms of the node values or the cell center values. We've done this one, the body forces term. So that's the volume integral terms done. So to complete the discretization, we have to do the surface integral. So on the continuity equation, we're summing the volume flow rate in and out of each point. That's this divergence essentially. So we have to do a surface integral here, and the advection gradient term here, and then summing the viscous forces, the surface forces. So once we do the surface integrals, then we're done. So let's start with the continuity equation. So like the diffusion term we did at the very, very start in the last of the slides, we'll start with a closed surface integral. And then if you have a closed surface integral, mathematically you can just split that into a sum of open surface integrals. So if I have a box and I have a closed integral around that box surface, I can just split that into the sum of 6 open integrals. So I can just sum what's flowing into each of the 6 faces and then just add them together. That's the same. So if I have a closed integral here, I can just say sum over all faces. If I have some cell in 3D space or 2D space, I can just sum over each of the faces, and for each face, just evaluate whatever this thing is at the face. So the normal of the face by the velocity at the face. So these might be functions varying in space. So I will show you that we can approximate that in the same way we did for the volume integral, by just evaluating this term at the center of the face, or the centroid of the face. So for each of these terms, this is the area vector. So take the magnitude of that, that's just the area itself, multiplied by the normal at the center of the face, multiplied by the velocity at the center of the face. So where did that come from? Well, I'm using a truncated Taylor series again. So I'm going to assume that whatever I'm integrating over, say the velocity here at the face, I'll assume that close to the face, I can approximate the velocity by the velocity at the center of the face, plus the gradient at the center of the face, extrapolating by any distance away. So if I'm at any coordinate x in the region of xf, which is the center of the face, I can just linearly extrapolate to get some value. That's an approximation. That's a second order approximation. So if we have an integration over a face, we have this first term and a second term, and like I did for the volume integral, you can show that this second term, the integral of this x minus xf, where xf is the center of face, you can show that goes to 0 by definition. For xf is if xf is the centroid. And then you're just left with the value of the center of face. So we're using exactly the same method we did for the volume integral, except we're doing it at a face and writing in terms of values at the center of the face. So that means if I'm on a structured grid like this, I will just sum over each of these faces. So if I go to this face to evaluate this term at the face, then I can just get the velocity at that face multiplied by that norm, and then I just have to multiply that by the area vector here, the magnitude of the area vector, and then just sum that term up for all 4 faces. And this is why the finite volume method can apply to any general grids, because nowhere here are we referring to a specific shape. We don't need specific shape functions for particular elements. We're just summing over faces, so it doesn't matter if there's 6 faces or 4 faces or 5 faces, or in 3D you could have 25 faces or something like that. Like you could have a football-shaped cell. You can just sum over all those faces. And this way it doesn't, both in the volume integral and the surface integral, we haven't specifically indicated what the shape is as long as it's a polyhedron or polygon. It's not fully strictly true. It can't be fully general. So they normally say convex polyhedron, convex polygons. Convex means just broadly ball-shaped. So for example, if our cell was an actual donut with a hole in the middle, then our analysis doesn't really make sense. So they have to be broadly ball-like, I would say. So they call them convex polygons, or call them convex polyhedron. So to complete the discretization, and by to complete it, I mean, remember, we're aiming to write all of these terms in terms of the values of velocity or pressure at these particular cell centers. So for example, if I'm at this face here, this is the velocity of that face, a simple approach will just say that the value at that face there is just the average of the center cell plus this, in this case, a north cell. So if I just average those, that will give us approximation there. In practice, they'll just do a linear interpolation. They'll basically just fit a line there and they'll do a weight based on relative distances. But you could do something more exotic as well. So the complete discretization, in this case, if we were just using simple averaging, we'll say that you sum over every face and take the area and the normal of that face and then multiply it by the average of the value there. And then that's how that term is calculated in terms of a particular computation stencil. So that's the continuity equation, and then we're going to do something similar for the advection term and the diffusion term. So surface integral is a closed surface integral. The first step we're going to do is write that as a sum over open surface integrals of all the faces. So I've skipped that step here, and I've then gone straight to doing this truncated Taylor series. So I'm going to say this term is approximately equal to sum over all faces multiplied by the area, and then just evaluate this term at the center of the face. So the center of the face, outward facing normal, and the velocity of the center of the face multiplied by the velocity of the center of the face. So this term is almost the same as the continuity equation, except we're multiplying by an extra velocity. Sometimes this area vector by one of the velocities, which represents a volume flow rate, meters cubed per second, they sometimes call that the flux. So often they mention fluxes in volume methods. This is, it represents a flow through a face. So if you say V flux, they're normally referring to this mass flow rate or volume flow rate in this particular term. So if we have VF here and VF there, we can evaluate VF, the velocity at a face, by averaging between the two cells that face travels. Or we can use something fancier. So if we just linearly interpolate it, which is the same as averaging if the face is exactly halfway between them. That's sometimes called central differencing. So when you do linear interpolation in finite volume textbooks, they sometimes call that central differencing. Even though there's no difference, it's actually just an interpolation. It's just equivalent to taking the difference. which is fine, you can do that. But they've noticed from numerical experiments and some analysis, you can show that that's not always stable. What I mean by stable is if you set up your solver to use this method and you can force Fluent to use it, that you might get oscillations in your solution. So in the finite element method, we looked at zero energy modes. We talked about hourglassing, where you can get like these oscillations in the displacement, where you have this numerical error. So the same thing, all numerical methods suffer from these same challenges. So you get zero energy modes in the finite volume method. If you use central differencing here, you will sometimes get checkerboarding style error. So you might get the pressures peaking, the velocities peaking cell to cell. So they normally will try and interpolate one of these velocities using a slightly different method to stabilize it in some. So one approach that is very stable is called the upwind method. So if we take this second velocity here, so we'll just call this something the flux that will be just averaged. But this second velocity here, the idea is you check which direction the flux is at this phase. And by flux, I mean literally the direction of velocity flow, which way the mass is flowing. So if it's a fluid problem. So if mass is flowing from this direction to this direction, then the idea with upwind is you check upwind and just use the value of the upwind node rather than the downwind. So in this thing here, this just represents the velocity multiplied by the phase. So if the if this is positive, it means fluid is leaving this cell. So that means upwind direction is the P node value. Whereas if it's negative, it means there's flow going back into the cell, in which case we'll use the NF value. And so that's called the upwind method. So the advantage of the upwind method, it's very stable. You will not get any of these oscillations in your grid. It tends to stabilize everything. It physically makes sense as well that, well, if something's flowing from this side to this side, then this side probably carries more information to that phase. That's the kind of reasoning. So upwind interpolation is stable, but it's first order accurate and highly dissipative. So what does that mean? It means that when you use upwind for this convection advection term, that it will reduce your order of accuracy of your entire method to first order, which means if you halve the mesh spacing, the error will halve. That doesn't sound that bad, but that's actually pretty poor. So it means you'll need very, very fine grids to get to the true solution if you're using the first order method. So in practice, you should really just not use upwind. People use upwind, but as in you'd have to use such a fine grid in most cases to get a true mesh independent solution that you really can't be sure that you're a fine enough grid. So there are second order versions of upwind. So rather than using the value at the upwind side, the node, you use the value there and its gradient to extrapolate to the phase. So you get an upwind effect, but it's higher order values. So in Fluent, if you go to solution methods and momentum, you'll be faced with something that looks like this. I think this is what it looks like. The version installed upstairs. They will slightly change it every version of the year, but it almost doesn't really change. So if you go to momentum, you will see, I think by default, actually, I'm not sure what the default is. I think second order upwind is the default. So you can go second order upwind or first order upwind. And so both of those should be stable. First order will be more stable, but it will produce a very large mesh error. And in terms of fluid mechanics problems, if you use first order upwind, it tends to just smear everything. So if a streamline wants to go sharply around the corner, it tends to just smooth it out and not let it go sharply around the corner. So it changes the solution quite a lot unless you have very fine mesh. You know, there are other methods. Third order muscle is another method, and the quick method, that's another acronym to it for a particular type of method, which I think is second order. So if we look over here, this is from this Hertziger and Parrish CFD book. They were looking at the heat flow through a particular boundary of a simple model, and they knew the true solution to be this line. And this is the number of control volumes or cells on a log scale, so 100, 1,000, 10,000, 100,000. And they looked at a second order method which is the black line. So in the half the spacing, the error reduced by a factor of 4, half it again reduced by a factor of 4, half reduced by a factor of 4. So you can see that the error is like going to 0 relatively quickly. But then the first order upwind method, initially you jump to here, then you jump to here, and then this is the asymptotic region. So you can see the error is going down quite slowly. So even on the very finest grid of 100,000 cells, the error is still quite large. So you have to be very careful of if you are using upwind, where you use it first order upwind. So why does it exist if it's a little bit, if I'm making it sound so terrible? Sometimes if you start with second order schemes in a CFD problem, from the start, everything just blows up. So what people often use is they'll start with first order schemes, highly distributed first order upwind. You'll get an initial flow field and it's stable. And then you stop the calculation, switch to the higher order schemes and restart them. So if you have a good guess, the second order schemes won't explode. So the idea is you start with the lower order schemes. In practice, what I would do is I just start with higher order schemes. If it works, great. I don't have to think about it. If it doesn't work, then I go back and I run with a lower order scheme and then restart with the higher order scheme. So that's the idea. So you have to be very careful. Sometimes some of the equations, like in turbulence equations, you can solve them at first order. Maybe it's okay. They don't affect the solution. Just be very careful. And in the time formulation, you'll see how they discretize the ddt, the acceleration term. I don't know what it defaults to here. I can't remember. I think it should be second order. But equally, you probably want to use second order. First order is normally just terrible. So they have second order and bounded second order. So generally, if you see a bounded version, it's normally just a little bit less accurate than the non-bounded version, but you get the benefit if it's a bit more stable, less likely to crash. That's the idea. And once again, you could start with the first order, get some initial solutions, and then switch to higher order. The last thing I wanted to do, yeah, it only takes a minute, is we had to just finish this pressure term. So we got this far with the volume integral and we had gradient of pressure. So how do you calculate gradient of pressure in terms of the surrounding stencil of nodes, of cell centers? So one approach is to use Gauss's theorems. Gauss's theorem is sometimes called the Green-Gauss or Gauss-Green theorem. So the idea is if you have a gradient of something, a volume integral of that, you can write that as the surface integral of replacing the grad in A. So it's the same thing we use to switch between volume and surface integrals, except without the dot. So then you can just sub pressure in there. And this volume integral on the left, we can integrate that just by the gradient of the cell center pressure by the volume. And then we can use our surface integration approach for the pressure on the right-hand side. And then we just divide across by 1 over the volume. So we can say the gradient of pressure at a cell center is 1 over the volume by sum over all the faces. So essentially tricked that volume integral into being like a surface integral to be able to do it. So if we go back to Fluent, the last thing just to finish on, you'll also see there's this gradient calculation, and they're specifically talking about the gradient of pressure. So you can see this green Gauss cell-based, that's that approach. But there's a formulation that you can kind of do it via the nodes or the vertices, which is fine as well. But normally, the most accurate on bad meshes tends to be least squares, where you fit a plane through all the surrounding cells. So all of those should be second order, but I suspect least squares is probably the only one. Maybe the node-based green Gauss is truly second order on bad meshes. And yeah, I'll leave the solution methodology for Wednesday. Okay, I'll send an announcement when I put up the assignment as well. Thank you. Yeah, cheers.